What's up guys, it's Simon Fiaz. Today's video is on AS Level Chemistry Paper 1 June 2017. Okay, question 1. Write the full electrical configuration for each of the following species. Cl minus, Fe2+. Now Cl minus, we'll look at chlorine, 17 electrons. But because it's a minus charge, I'm going to add another one. So it's going to become 17 plus 1, which is 18 electrons. Now, I can, do this. 1s2, 2s2, 2p6. 3s2, 3p6. I think that's too much, so let's count. 4, 10, 12, 18. Nope, that's just perfect. Fe2 plus. Look at iron, and it has got 26 electrons, but because it's a 2 plus, I'm going to minus 2, so it's going to be 26 minus 2, which is 24. So it's going to be the exact same as Cl minus, except now that I need to add another 6 electrons. So 3p6, 4s2, 4p6. Well, that will give me to 26, and that's not what I want. I want 24. So 4, 10, 12, 18, 20, 26. So 4p4, right? But then that will... Well, then that's partially empty. So what I'm going to do instead is that this goes, and then I've got 3d6. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Write an equation represent when third ionization of manganese is measured. So manganese is, I don't even know the formula, Mn. Okay, so it's going to be Mn 3 plus gaseous plus E minus arrow here, Mn 2 plus gaseous. That's simple. Say which of elements magnesium aluminium has the lowest first ionization energy. Magnesium aluminium. Now I know first ionization energy increases across a period, but if I look at magnesium, 1s2, 2s2, 2p6, 3s2, how many electrons we got? 12, 4, 10, 12. Whereas with aluminium, 3s2, 3p1. So even though it is, it's got more electron, but that's in a different orbital. So that's what I'm going to be talking about. So aluminium has a lower first ionization energy. Aluminium. The outer electron is in a what kind of orbital? Don't just say p orbital. You need to be very specific. Outer electron is in 3p orbital. Therefore, it is higher in energy. Actually, higher in energy slash further away from the nucleus, so easier to remove. 1.4. Give a symbol including mass number of the iron that would reach the detector first. I know it's a sample of nickel, and it's an iron, so it's going to be Ni plus 58. And it's 58, so 58 Ni plus, something like that. Yeah, because it's done by electron impact ionization energy anyway. Calculate relative atomic mass of the nickel. So all I'm going to have to do here is I'm going to do 58 times by 61 plus 60 times by 29.1 plus 61 times by 9.9, and I always would double check in my calculator to see if this adds up to 100, but I can already always check, but I can already see this case it does, because 61.0 plus 9 will give me 70, and then 70 plus 29.1, it would give me 100. So divided by 100, and I should get 58 point, what do I want it to? 1 decimal place, 58.9. And it's these small details, like if you don't give it to 1 decimal place, you're probably going to lose a mark. If you don't show your method, you're probably going to lose a mark. So it is 3 marks, but you have to be very, very specific. Question 2.1. Write an equation including state symbols for the reaction with an enthalpy change equal to enthalpy of formation for iron 3 oxide. Iron 3 oxide. Well, if I look at iron 3 oxide, so I know I've got iron, Fe with a 3 plus charge, oxide, O2 minus. So if I swap the charges, it just becomes Fe2O3. That's a way to know it if you didn't know it. So Fe2O3, entropy of formation. So I'm forming that. And what is that? That's a solid. So I've got Fe solid plus O2 gaseous. Obviously I need to balance it out. I need 2 here and I need 3 over 2 here. 2 Fe solid plus 3 over 2 O2 gaseous arrow Fe2O3 solid. Table 2 contains some standard entropy of formation data. Uses data and equation for the reaction of iron 3 oxide with carbon monoxide to calculate value for standard entropy of formation. So, okay. Standard entropy of formation for carbon monoxide. Okay, so I know delta H is minus 19, so I'm going to set the equation. Minus 19 equals, well, iron is always going to be, that's going to be 0, so plus 3 CO2. I'm going to find for carbon dioxide, yeah, so it's going to be minus 19 equals, well, because it's entropy of formation, entropy of products minus entropy of reactants, so it's going to be minus 19 equals 3y minus entropy of reactants, so minus 822 plus minus 333. How do I know that? Because this is minus 1111, 111, and I've got 3 of them, so I just times it by 3. Now if I put this in my calculator, minus 1155, and then I add that, because so what I'd get is minus 19 equals 3y minus 1155, and that's basically adding it, and then I subtract in this hand side, so I get 3y equals minus 19 minus 1155 minus 1174, and then I get y as my answer divided by 3, which is minus 391 kilojoules multiplied minus 1. Use the data from table 3 to calculate bond entropy for NH in ammonia. Okay, bond entropy, energy required to break bonds minus energy released when new bonds are formed. And I know okay, so I know to go from N2 to 2N, so the answer is, okay. So I've got, okay, so first thing I would do is actually draw out ammonia, and you realize you've got 3 NH bonds, but then you've got this 2 here, so that becomes 6 NH bonds. So I'm going to say 6 bracket NH, that's what I'm trying to find, equals energy required to break bonds minus energy released when new bonds are formed. Well, energy required to break bonds is this. Go from N2 to 2N, so it's going to be 944 plus 436. But the thing about 436 is that's for 1 mole. I've got 3 here, so it's going to be 436 times by 3. Minus energy required to break bonds, which is, you can see, because I'm going from N2 to 2N, I'm breaking the bonds. H2 to 2H, I'm breaking the bonds. Energy required to break bonds minus energy released when new bonds are formed, minus 92. I've got 2 negative, that becomes positive, and then that will give you for 6 NH, and then you just divide it by 6. So then therefore NH is just that divided by 6, and you should get 391, and always clarify that it is positive. Give one reason why the bond entropy You calculated in question 2.3 is different from the mean bond and 3/4 in a data book. Data book values derived from a number of different compounds. Is derived from a number of different compounds. Yeah, that's it. Data book value is derived from a number of different compounds. Question 3.1, show by calculation which reactant was in excess. And it tells me that measuring some that used to transfer that much of zinc sulfate into a glass beaker, blah blah blah. So I can already tell it's going to be magnesium and the Zn2 plus. So first thing I'm going to do is do the easier thing that I can spot moles of magnesium. 2.08 divided by the MR, which is 24.3. Then I need to find out the moles of zinc sulfate, which is, I'm going to use concentration and volume, 50 divided by 1000 times by 1.00. And I get here, I get 0.856, 0.0856, sorry, and here I get 0.050. So which reactant is in excess? It is going to be, which reactant was in excess? Magnesium. Yeah, clearly magnesium. 0.050, 0.0856. And then it says use the data to calculate experimental value for enthalpy of reaction kilojoules per mole to power minus 1. And okay, this is going to be a lot different from what I'm expecting. So, enthalpy of reactions. First things first, Q equals MC delta T. Delta H is Q divided by moles. And that's what I'm trying to find. I'm trying to find enthalpy of reaction. So I need to find out Q first. Q equals the mass. The mass of what exactly? Well, I know density of solution 1 gram per centimeter cubed. How many? 50 centimeters cubed. So it's going to be 50 times by 4. Is it 4.18? Yeah, it's always 4.18. Specific heat capacity times by temperature change, which is going to be 61.2 minus 23.9. 61.2 minus 23.9. Now, obviously, Q is measured in joules. So I am going to have to divide my answer by 1000 because I want my final answer kilojoules. Now, to work out the moles, what am I working out the moles of exactly? Well, I've already got the moles of that. So what I'm going to do now is, because I know the moles of magnesium is in excess, I don't care about it. I'm going to use the moles of zinc sulfate. So it's going to be Q divided by 0.05. 0.05. And obviously I do Q divided by 1000, and you should get minus 156 kilojoules per mole to power minus 1. And yeah, that's it. Obviously you don't actually get a negative, because if I put in a calculator 50 times by 4.18 times by 61.2 minus 23.9 divided by 0.05 and then divide my answer by 1000, I get 156. But the reason I add this negative sign is because if I look at this, starting temperature of that, maximum temperature of that, so what happens to temperature? Temperature increases as temperature increases. And what does that tell me? Exothermic reaction. Question 3.2 suggests the most likely reason for the large difference between each student's experimental value. The data book value, heat loss should be fine. Heat loss. Suggests that the student's method could be improved in ability to determine more accurate value for the enthalpy of reactant. Okay, so first things first. It tells me do not refer to precision of the measuring equipment, do not change your equipment. So first things first. Stage 1, always improved insulation. Stage 1, improved insulation. So, insulate the beaker. Insulate the beaker / use a polystyrene cup to, what do I do that for? To reduce heat loss. Stage 2, improved temperature recording. Record the temperature for a suitable time before adding. This is before you add the metal. And what this does is establishes accurate initial temperature. And stage 3, improved analysis of results. Extrapolate cooling back to the point of addition to establish a maximum temperature. That's it. Stage 1, insulation, improved insulation. Use insulate beaker / use a polystyrene cup / use a lid. And all of these are designed to reduce heat loss. Stage 2, improved temperature recording. Record the temperature for a suitable time before adding the metal, establishing accurate initial temperature. Stage 3, improved analysis of results. Extrapolate cooling back to point of addition, establish a maximum temperature. Question 4. Deduce in terms of X amount of moles of R in the equilibrium mixture, and it tells me that 1 mole of P and 1 mole of Q are mixed in the container with this much volume. At equilibrium, X amount of P had reacted. So let's put that into the ICE method. ICE, initial moles, CM, change moles, equilibrium moles, and I've got P, Q, and R. The only different thing about this question is we've got algebra, we've got X, X. So it's going to be definitely a bit more complicated. So I've got initially 1 mole of P, 1 mole of Q. Then it says equilibrium moles is of equilibrium X moles of P had reacted. So X here of P. So how do I go from 1 to X? Well, I'm gonna do 1 minus X. And if I do, actually no, what is it? To go from 1 to X. If I'm trying to go from 1 to X. X minus 1. Anyway, I think I'm overreacting because I know it's a 1 to 2 mole ratio. So if I've got X moles here, I've also got X moles here. And for R, initially it doesn't tell me. I'm going to assume it's 0. For the equilibrium mole is just going to be 2X. So yeah, that's another way of doing it. 2X. Using the mole ratio 1 to 2. And I've got X moles of P, therefore I'm going to have 2X moles of R. Then it says calculate value equilibrium concentration moles per minus Q R, and I know Kc. The key thing about Kc is obviously square brackets, and Kc is R squared P over Q. It's already given me it. So we want me to calculate value for the equilibrium concentration of R. So I'm going to have to rearrange it to get R. So it's going to be concentration of R equals square root of Kc times by concentration of P times by concentration of Q. And yeah, I know Kc is 3.6 times by concentration of P. Well, I don't actually know the concentration of P. I'm given the X moles of P had reacted. Okay, I've not done the right thing. What I should have done, well, I'm going to do it now, obviously, is the idea that I can't do that because I'm not given actual moles, I'm given X and that. So first thing I'm going to have to do is find out what is X. So I'm just going to substitute the value. Kc 3.6. Concentration of R squared is just going to be 2x squared divided by P and Q. So divided by P and Q, which is just going to be, well, I know moles of each of P and Q at equilibrium is 1 minus X of each P and Q. So it's just going to be 1 minus X squared. Now I need to rearrange it. So what I would do is square root both sides. I get square root of 3.6, that cancels out. Then times by that, so I get square root of 3.6 minus square root of 3.6x equals 2x. And then I guess add x and then you should get, because if I do 2 plus root of 3.6, I get that. And then I get like 3 point something x, and then I do root 3.6 divided by my answer, and I get 0.49, which is, yeah, correct. So just do that. You get x is 0.49. However, I know that the moles are an equilibrium mixture is 2x. Therefore, the equilibrium concentration of R is just going to be 0.49249 times by 2. And what is that? That's going to be 0.97. Give the meaning of the term electronegativity. The power of an atom to attract a pair of electrons in a covalent bond. The power of an atom to attract a pair of electrons in a covalent bond. Explain how permanent dipole-dipole forces arise between hydrogen chloride molecules. Okay, let's do that. Well, the first thing is the differences in electronegativity leads to bond polarity. The dipoles don't cancel out. Molecule has an overall permanent dipole attraction between delta positive on one molecule and delta negative on another. So differences in electronegativity leads to bond polarity. That's very important. Dipoles don't cancel out, therefore molecules are overall a permanent dipole. Attraction between delta positive on one molecule and delta negative on the other. Complete table 4 by naming the shape of each molecule. Place it in the final column if the molecule has a permanent dipole. So I'm going to do the second one first because I think that's a bit easier. So SiH4 definitely does not have a permanent dipole, it's completely symmetrical. pH3 will. BeCl2 completely symmetrical. CH3Cl definitely will. So that's pretty nice. Now the naming of the shape, this is how well you know your knowledge. So SiH4 is going to be tetrahedral. pH3 tetrahedral. Pyramidal actually better. Tetrahedral pyramidal. BeCl2 very easy. Linear. CH3Cl tetrahedral. Or you could say distorted tetrahedral, but tetrahedral should be fine. So SiH4 tetrahedral, pH3 pyramidal, BeCl2 linear, CH3Cl tetrahedral. And then obviously if a molecule permanent dipole, pH3 and CH3Cl have permanent dipoles. Question 6.1, balance equation for the two stages in this process. CuFeS2 plus O2 plus SiO2, and then something else. So just balancing it out really. So you should get 4, 9.5 here, 4 here, 7 here, 4 here, 2 here, 6 here, and that's it there. If I try to do it, that would take me ages. So I'd probably leave this question to last, or at least near to the last. So just 2 reasons why sulfur dioxide is removed from exhaust gases. It prevents acid rain, because remember sulfur dioxide will cause acid rain. It's toxic / causes breathing problems. So one reason prevents acid rain. Another reason is that it's toxic / causes breathing problems. Question 6.3. A passenger jet contains this much of copper wiring. A rock sample contains this much of copper CuFeS2 by mass. Calculate the mass in tons of rock needed to produce enough copper wire for passenger jet. Okay. A passenger jet contains this much of copper wiring. A rock sample contains this much of that by mass. Calculate mass in tons of rock needed to produce enough copper wire for passenger jet. So what I would do first is work out the moles of the copper wiring. So let's just do that. Ready? So first thing first, find out the moles of copper. Now, obviously, I need it in grams. I don't care about it in being. I do care about it being kilograms, but I need it in grams. How do I convert from kilograms to grams? I times by 1,000. Divided by the MR, 63.5 of copper. Okay, that's the moles of copper, right? And then I get the moles of 6, 3, 7, 8, and 0. Now I've got that, I can find out the mass of this because 1 to 1 molar ratio. Sorry, that's the moles of that, so I can work out the mass of that now. So then I work out the mass of CuFeS2, which is 63780 times by the MR. Use a periodic table, 183.5, and you should get 1.17 times by 10 to the power 7. Now the units are going to play a really important role. Is this in grams or kilograms? It's going to be in grams, right? Because first thing I did is I converted the moles of the mass of this in grams. Then I use this to work out this. Therefore, this is always going to be in grams. The mass, moles of mass of MR. But I don't want that. I want the mass of rock needed to produce enough copper wiring. So first thing I'm going to have to do is I know a rock sample contains this much by mass. And I want to find out the mass of rock. And I've got the mass of CuFeS2. So what I'm going to do is I know rock sample contains this much of that by mass. So I'm going to do 1.17 times by 10 to the power 7 times by 100 divided by 1.25, and then that will give you the mass ore. So 1.17 times by 10 to the power 7 times by 100 divided by 1.25, and then obviously divided by 1,000, divided by 1,000, 936. So I want it in tons. So first thing I do is that's mine's in grams. I convert it to kilograms by divided by 1,000, and convert it to tons by divided by 1,000. Divided by 1,000. Calculate percentage atomic economy for the production of copper in this process. Now, percentage atomic economy MR of desired products over MR of all reactants times by 100 for the production of copper. So copper is 63.5. But I'm going to include, with percentage atomic economy, I always include the moles. So it's going to be 63.5 times by 2 over 2 times by 63.5 plus 16 plus 12 is a percentage times by 100. 63.5 times by 2 all over 2 times by 63.5 plus 16 plus 12 times by 100. 74.3. Just testing. Do you know the formula? M of desired product over MR reactants. And do remember that you have to times by the number of moles as well for the MR. And that's really it. Question 7. Suggest the identity of the group 2 metal ion present in solution Y. And it says, so with sulfuric acid, a white precipitate forms. With magnesium nitrate, a white precipitate forms. Write the ionic equation for the reaction that takes place when sulfuric acid is added to solution Y. So it's clearly going to be Ba2 plus, because how else can, because we're acting with sulfuric acid and a white precipitate. Then it's going to be Ba2 plus aqueous plus SO42 minus aqueous to form BaSO4 solid. Ba2 plus aqueous plus SO42 minus aqueous to form BaSO4 solid. Suggest the identity of the negative ion present in solution Y. One type of negative ion, it's going to be OH minus when magnesium nitrate is added to solution Y. So magnesium nitrate, ionic equation, I only care about the ions. So it's going to be Mg2 plus aqueous, so magnesium, plus OH minus aqueous, and what do I need here? I need a 2 here to form MgOH squared magnesium hydroxide solid. Question 8.1, and then all of this. So let's just review this. Question 7.1, Ba2 plus aqueous plus SO42 minus aqueous to form BaSO4 solid. 7.2, negative ions generally always going to be OH minus ions. And then ionic equation, I only care about the ions, that's why I call it ionic equation. So with magnesium nitrate, I only care about Mg2 plus aqueous, and then plus OH minus to form MgOH squared. I need a 2 there as well to form a solid. So give the oxidation state of nitrogen following species. NO2 minus, well, oxygen minus 2 times by 4 minus 4, so that's going to be plus 3, and here is going to be plus 2. Right, half equation for the conversion of NO2 minus in acidic solution into NO. First thing I can realize is I've got 2 oxygens left hand side, 1 oxygen right side, so I need to add a H2O molecule. But now I've got 2 H pluses, so now I need to add 2 H pluses here. And then I also need to add a negatively charged electron. Now let's see if it's balanced. 1 nitrogen, 1 nitrogen, 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens, yes. And is the charges balanced? Yeah, overall charge is 0 on the left hand side, minus 2 plus 2, 0, overall charge is 0 on the right side. Round the half equation for the conversion of I minus into I2. Well, first things first, I've got 2 iodines on the right side, so I need a 2 here. Then, because I want to balance the charges, I just need to add 2 negatively charged electrons here. Write an overall ionic equation for the reaction of NO2 minus and acidic solution with I minus. So what I'm going to have to do here is I can see that I've got 1 electron, negatively charged electron here, 2 here. So I need to times this whole equation by 2. That will give me 2E minus plus 2H plus, no, sorry, plus 4H plus 2NO2 minus R2NO plus 2H2O. Let me just check if I even got part 2 and part 3 wrong. Right, so plus 3 plus 2, NO2 minus plus E minus plus 2H plus NO plus H2O, 2I minus RI2 plus 2 minus, perfect. And then what I do is, then I realize, okay, the electrons cancel out now. Obviously, don't do that in the exam because that's part of your answer to 8.3. And then you just add them on. So then it's just going to be 4H plus 2NO2 minus plus 2I minus arrow 2NO plus I2 plus 2H2O. I thought we could divide by 2, but obviously I can't because there's 1 there, iodine. So 2NO2 minus plus 4H plus 2I minus to form 2NO plus 2H2O arrow plus I2. State the role of NO2 minus in the reaction with I minus. State the role of NO2 minus in the reaction with I minus. It's going to be an oxidizing agent. Oxidizing agent. Question 8.6. An aqueous solution, nitrite ion reacts with acidified chlorate, 5 ions according to equation. 25 centimeters cube sample of aqueous solution sodium nitrite. Require this much of potassium chloride. Calculate concentration grams per dm minus cube of sodium nitrite in the sample. So first thing I would do is find out the moles of so find out the moles. So 27.4 of concentration of volume times by 0.0200. That will give me 5.48 times by 10 to the power minus 4. And that is the moles of the ClO3 minus, right? Because the potassium chloride, but it's obviously the aqueous solution, so it's dissolved in ClO3 minus. That's the moles of this. I want to find out the concentration of sodium nitrite. So I want to find out the moles of these NO2 minus ions. So first thing I'm going to do is I'm going to do 5.48 times by 10 to the power minus 4 times by 5 over 2. That will give me 1.37 times by 10 to the power minus 3. Why do I do that? Because it's 2 to 5 molar ratio. Then, because now I've got the moles of sodium nitrite, I know the volume is this, I can find the concentration. Because moles is concentration, volume, concentration is going to be the moles, which is what I worked out, 1.37 times by 10 to the power minus 3, divided by the volume, 25 times by 10 to the power minus 3. Put in a calculator. I get 0.0548 moles per dm minus cubed. And now this final part I think is the trickiest, in grams per dm minus cubed. But how do I go from moles per dm minus cubed to grams per dm minus cubed? Because obviously this is in moles per dm minus cubed concentration. All I have to do is times by the mR. So I need to times by the mR of sodium nitrite. So it's going to be 69. It's not going to be 14 plus 16 plus 16. I also need the sodium. So times it by 69. So remember, to convert from moles per dm minus cubed into grams per dm minus cubed, you need to do the moles per dm minus cubed times by the mR. So 0.0548 times by the 69 to give me 3.78 grams per dm minus cubed.